Hello everyone, welcome to my YouTube channel. In previous video we have discussed few important questions on division by T property. Now in this video I am going to take two important questions on division by T property which are frequently repeated in various university examination. So the first question is, find the Laplace transform of sin AT by T. Next part of this question is, does the Laplace transform of cos AT by T exist? And also deduce the integral 0 to infinite sin T by T equal to pi by 2. Using the technique of Laplace transform. So this question has three parts, so we take one by one. So in first part we are going to find the Laplace transform of sin AT by T. So the first part is to find Laplace transform of sin AT by T. And since here the function sin AT divided by T, so to find its Laplace transform, we use division by T property. First we assume sin AT is ft and then find its Laplace transform, which we denote by f bar s. And then to find the Laplace transform of sin AT by T, we use division by T property of Laplace transform. So we start by assuming let ft is sin AT, then its Laplace transform, that is Laplace transform of ft, is a upon s square plus a square, which is the formula of Laplace transform of sin AT and which we denoted by f bar s. So we get Laplace transform of ft is f bar s. Now by division by T property we know that if Laplace transform of ft is f bar s, then Laplace transform of ft by t is the definite integral s to infinite f bar u du, where f bar is Laplace transform of ft. So using this property we get the Laplace transform of ft by t. Here ft is sin AT, so Laplace transform of sin AT by t is given by the definite integral s to infinite f bar u. So f bar s is what? A upon s square plus a square. So f bar u is what? A upon u square plus a square du. So this is the division by T property by which we get the Laplace transform of sin AT by t. Now we integrate this integral. So we get a is constant, so as it is, integration of du upon u square plus a square, like dx upon x square plus a square is what? 1 upon a tan inverse x by a. So the integral of du upon u square plus a square is 1 upon a tan inverse u by a. The limit of integration is s to infinite. Here a to a cancel. Now we put upper and lower limit in place of u. So upper limit gives tan inverse infinite and lower limit gives tan inverse s by a. So we get tan inverse infinite minus tan inverse s by a. Now tan inverse infinite is what? Pi by 2. So tan inverse infinite is pi by 2. So pi by 2 minus tan inverse s by a. And pi by 2 minus tan inverse s by a is what? Cot inverse s by a. So we get Laplace transform of sin AT by t is cot inverse s by a, and which is also equal to tan inverse a by s. So this is the Laplace transform of sin AT by t. Now in second part we are going to find the Laplace transform of cos AT by t, and we find whether the Laplace transform of cos AT by t exists or not. So the second part is to find Laplace transform of cos at by t. So here the function cos at is divided by t. So to find its Laplace transform, we use division by t property of Laplace transform. First we assume cos at is ft and then we find its Laplace transform, which we denote by f bar s, and then to find the Laplace transform of cos at by t, we use division by t property of Laplace transform. So we start by assuming ft is cos at, then the Laplace transform of ft is s upon s square plus a square, which is the formula of Laplace transform of cos at, and we denote Laplace transform of ft by f bar s. Now from division by t property we know that if Laplace transform of ft is f bar s, then Laplace transform of ft by t is what? Definite integral s to infinite f bar u du, where f bar is Laplace transform of ft. So using the division property we get Laplace transform of cos at by t. ft is cos at, so ft by t is definite integral s to infinite f bar u. F bar s is what? S upon s square plus a square. So f bar u is what? U upon u square plus a square du. So this we apply the division property of Laplace transform to find the Laplace transform of cos at by t. Now we are going to integrate this, and for that we multiply and divide this integral by 2, and we get 1 by 2 s to infinite 2u upon u square plus a square du. So here we multiply and divide this integral by 2. Now if we put u square plus a square equal to t, then we get 2u du equal to dt. So the integral take the form of dt by t. If u square plus a square is t, then 2u du equal to dt. So dt by t. And what is the integral of dt by t? Is log t. So the integral of this integration gives 1 by 2 constant multiple as it is. Now integration of this expression is log t, and what t is? U square plus a square. So we get log of u square plus a square, and the limit of integration is s to infinite. Now we put upper and lower limit. We get for upper limit u tending to infinite. This is u. U tends to infinite. Log of u square plus a square minus lower limit gives log of s square plus a square. Now this limit gives infinite. So we get 1 by 2 infinite minus log s square plus a square. So as a result of this expression, infinite minus something is infinite and divided by 2 is again infinite. So we get the Laplace transform of cos at by t is infinite. That means the Laplace transform of cos at by t does not exist. So we see the Laplace transform of sin at by t exists, but the Laplace transform of cos at by t does not exist. Now in the third part of this question, we are going to find the result of an integration 0 to infinite sin t by t dt. So in third part, we are going to prove the integral 0 to infinite sin t by t dt equal to pi by 2 using the technique of Laplace transform. So how we do this? By the technique of Laplace transform. So first we have Laplace transform of sin at by t is tan inverse a by s from first part of this question. Now if this function is ft, then what is Laplace transform of ft? Laplace transform of ft is given by the integral 0 to infinite e raised to minus st ft dt. the standard definition of Laplace transform. So in left hand side we apply the definition of Laplace transform, which is 0 to infinite e raised to minus st into ft. So sin at by t dt equal to tan inverse a by s. Now since we have to find integral sin t by t, so here we adjust the parameter a equal to 1, by which we get sin t by t, and the parameter s 0, so something power 0 is 1. So by assuming s equal to 0 and a equal to 1, we get, so this e raised to 0 is 1 and sin t by t as a is 1. So this integral take the form 0 to infinite e raised to 0 is 1 sin at a is 1, so we get sin t by t dt equal to tan inverse a by s. So a is 1 and s is 0, and something upon 0 is infinite, so we get tan inverse infinite. And what is the value of tan inverse infinite? Is pi by 2. So we get 0 to infinite sin t by t dt equal to pi by 2. So this is how, by using the technique of Laplace transform, we can evaluate certain definite integral. So this is an important question which is frequently repeated in various university examination. Now we take another important questions which is also repeated in various examination. So the next question is, find the Laplace transform of 1 minus cos t divided by t square. So here the function 1 minus cos t divided by t 2 times. So in order to find its Laplace transform, we have to apply division by t property 2 times. First we assume ft function is 1 minus cos t, and then find its Laplace transform f bar s, and then we apply division by t property to get Laplace transform of 1 minus cos t by t. Then we denote 1 minus cos t by t is the function gt, whose Laplace transform we get is g bar s. Then again we apply division by property 1 minus cos t by t divided by t, and then we get the Laplace transform of 1 minus cos t by t square. So here we have to apply division by t property 2 times. So we start by assuming ft function is 1 minus cos t. Now the Laplace transform of ft function is, Laplace transform of ft is Laplace transform of 1 minus cos t. Here we apply the linear property of Laplace transform. So by linear property we get Laplace transform of ft is equal to Laplace transform of 1 minus Laplace transform of cos t. And as we know, Laplace transform of 1 is 1 by s, and Laplace transform of cos at is s upon s square plus a square, and here a is 1, so the Laplace transform of cos t is s upon s square plus 1. So here the Laplace transform of ft is 1 by s minus s upon s square plus 1, which we denoted by f bar s. Now we apply division by t property, which states that if Laplace transform of ft is f bar s, then Laplace transform of ft by t is the definite integral s to infinite f bar u du, where f bar is Laplace transform of ft. So using the division property of Laplace transform, we get the Laplace transform of ft by t, and ft is what? 1 minus cos t. So the Laplace transform of 1 minus cos t by t, using the division by t property, we get integral s to infinite f bar u, f bar s is what? 1 upon s minus s upon s square plus 1. So f bar u is 1 upon u minus u upon u square plus 1 du. Now integrate this expression, we get s to infinite 1 upon u du is first integral, and second integral is u upon u square plus 1 du. So here we multiply and divide by 2 this expression to obtain its integral. Now the integration of du by u is log u, and here if we put u square plus 1 is t, then we get 2u du equal to dt. So dt by t, integral of dt by t is log t, and what is t? U square plus 1. So the integral of this expression is 1 by 2 log u square plus 1, and the limit of integration is s to infinite. Now 1 by 2, using the property of log, this 1 by 2 goes in the power of this expression, and power half is root. So we get log u minus log square root of u square plus 1. The limit of integration is s to infinite. Again use the property of log, that log m minus log n is log m by n, and we get log u upon square root of u square plus 1 s to infinite, the limit of integration. Now we put upper and lower limit, but the upper limit infinite gives infinite upon infinite form, that is undefined form. So to resolve this undefined form, we take u square common in the denominator. So we get u outside the sign of square root, and then u to u cancel, and in the sign of square root we get 1 plus 1 upon u square. So we have log of 1 upon square root of 1 plus 1 upon u square. The limit of integration is s to infinite. Now put upper limit infinite, we get 1 upon 1 plus 1 upon infinite. So 1 upon infinite is 0, 0 plus 1 is 1, and square root of 1 is 1, 1 by 1 is 1. So upper limit gives log 1, and the lower limit u equal to s gives log of 1 upon square root of 1 plus 1 upon s square. So upper limit and lower limit gives this expression. Now log 1 is 0, so we have 0 minus log of s upon, here s square is LCM, so we get s square plus 1 upon s square, square root, and the LCM s square, the square root of s square is s, which goes in the numerator. So we get minus log s upon s square root of s square plus 1. Now with help of this negative sign, using the property of log, this negative sign goes in the power of this expression, and the inverse power invert this expression, and we get Laplace transform of 1 minus cos t by t is equal to log of square root of s square plus 1 by s. So this is the Laplace transform of 1 minus cos t by t. Now we assume this function is gt and its Laplace transform is g bar s. So if gt is 1 minus cos t by t, then its Laplace transform g bar s is log of s square, square root of s square plus 1 by s. Now again we apply the division by t property in this gt function. We get Laplace transform of gt by t is definite integral s to infinite g bar u du, where g bar is Laplace transform of gt. So using the division by t property in gt function, we get Laplace transform of gt, which is 1 minus cos t by t divided by t, gt by t, is equal to definite integral s to infinite g bar u G bar s is what? G bar s is log of square root of s square plus 1 by s. So G bar u is what? Log of u square plus 1 by u. So we have s to infinite log of square root of u square plus 1 by u du. Here we apply the property of log, that log m by n is log m minus n. So the Laplace transform of 1 minus cos t by t square is s to infinite log of square root of u square plus 1 minus log of u du. Now we separate two integral and we get first integral is s to infinite log of, here the square root is power half, so we get log of u square plus 1 power half, and using the property of log, power goes in the multiplication term, we get 1 by 2 s to infinite log of u square plus 1 du minus second integral is s to infinite log u du. Now we assume this two logarithmic term multiple by 1. So this is your logarithmic term first part and this is algebraic term second part. So we integrate this expression using the integration by part technique. First part is log and 1 is second part. Similarly, in the second integral, log u is the first part and 1 is second part. So we integrate these both integral using integration by part technique, and we get 1 by 2 as it is, constant multiple. First as it is, that is log u square plus 1, integration of second, integration of 1 is u s to infinite minus sign of integral s to infinite, differential of first, so differential of log u square plus 1 is 1 upon u square plus 1 into 2u and multiplied by integral of second is u, so u into u square, so we get s to infinite 2u square upon u square plus 1 du. Similarly, the second integral gives first part log u as it is into integral of second, so integral of 1 is u s to infinite minus sign of integral, differential of first, so differential of log u is 1 upon u into integral of second is 1, so integral of 1 is u, so u du. So this is, we integrate these two integral by using the technique of integration by part. In next step we write u to u cancel, so du only in this integral, and in this integral 2 is constant multiple, so we write outside the sign of integral and we have u square in numerator, then we add and subtract 1 in numerator, so we get 2 into s to infinite u square plus 1 minus 1 upon u square plus 1 du. So our next step become 1 by 2 u log of u square plus 1 s to infinite as it is minus 2 into s to infinite u square plus 1 minus 1 upon u square plus 1 du minus u log u s to infinite minus s to infinite, u to u cancel, so we have du only. Now in this integral we separate the LCM, so u square plus 1 upon u square plus 1 cancel, so we get 1 minus 1 upon u square plus 1 du. So the next step is 1 by 2 u into log u square plus 1 s to infinite we write as it is minus 2 into, we separate the LCM and we get 1 minus 1 upon u square plus 1 here du, and the rest term is as it is. Now we integrate these two integral, we get 1 by 2 u into log u square plus 1 minus 2 into integral of 1 is u minus integral of 1 upon u square plus 1 with respect to u is tan inverse u, and the limit of both is common s to infinite, so we'll write common limit s to infinite, minus in this expression we have u log u minus integral of du is u, and we write the common limit s to infinite. Now from these two expressions, since 1 by 2 is multiplied only by this term, we take 1 by 2 common from these two terms and we get 1 by 2 common, so we have u log u square plus 1 minus 2u minus minus plus 2 tan inverse u minus, here 1 by 2 is absent, so we multiply and divide by 1 by 2, and 1 by 2 is common, so we have two multiple term here. So we multiply this expression by 2, we get minus 2u log u minus minus plus 2u, and the common limit of these two expressions s to infinite. Now negative 2u and positive 2u cancel, so we get 1 by 2 u log u square plus 1 plus 2 tan inverse u minus 2u log u s to infinite. Now from these two terms we take u common and we get 1 by 2 u common, so we have log u square plus 1 minus, here u common, so we have minus 2 log u plus 2 tan inverse u s to infinite, the limit of integration. Now here this 2 goes in the power of u using the property of log, and we have log m minus log n is log m by n, so we get 1 by 2 u log m by n, so u square plus 1 upon u square plus 2 tan inverse u s to infinite, the limit of integration. Since u square plus 1 by u square, we can write 1 plus 1 upon u square by separating the LCM. So we write 1 by 2 u into log of u square plus 1 by u square, we write 1 plus 1 upon u square plus 2 tan inverse u s to infinite. Now we put the limit of integration in this expression. We get 1 by 2 upper limit u tends to infinite, u log of 1 plus 1 upon u square plus 2 tan inverse infinite minus lower limit s gives s log 1 plus 1 upon u s square minus 2 tan inverse s. So we put here the upper and lower limit. Now u tending to infinite gives 1 upon infinite 0 plus 1 is 1, and then we get log 1 multiplied by u tending to infinite. But log 1 is 0, so 0 multiplied by anything gives 0. So we have 1 by 2 0 plus, from these two terms we take 2 common and we get 2 into tan inverse infinite minus tan inverse s minus s log 1 plus 1 upon s square. Now tan inverse infinite is pi by 2, and we multiply this 1 by 2 in this bracket, so we get 2 to 2 cancel and we get pi by 2 minus tan inverse s minus s by 2, because of multiplied by 1 by 2 we have s by 2 log of 1 plus 1 upon s square. Now pi by 2 minus tan inverse s is what? Cot inverse s. So we get finally the Laplace transform of 1 minus cos t by t square is equal to cot inverse s minus s by 2 log of 1 plus 1 upon s square. So this is the Laplace transform of 1 minus cos t by t square. So here we applied the division by t property twice, to get the Laplace transform of 1 minus cos t by t square. So this is lengthy questions but very important. In next video we will discuss two more important properties of Laplace transform, which are Laplace transform of the derivative and Laplace transform of integral. So see you in next video. Thank you.